otherwise known as the pizza disc bed, which it was famous for a lot of years. Guy Bond described this, of course. And then in 2010, I think it was, or 2012, Alex Liu and I discovered the small baby fronds, which are actually all over the surface, which have been walked over for many, many years. It was actually slightly an accident in that I was here with a trip with Guy, and he was demonstrating the big pizza discs, and everybody, as you'll have to, was stood on the side, and I just happened to be stood right in front of a tiny little frond and a filament, which I sat upon for a season until the guys came back. I didn't tell Guy. I don't think he knows this story unless it's been videoed. Oh yeah, there you go.
Let's hope there are no tapes.
It's totally taped. Which we then described.
An illusion there.
The fantastic thing about this is that we'd already started describing the Ives Hediye morph story, which I think most of you probably know about. In which, because there is no real scavengers on the Ediacaran seafloor, things that died basically stayed where they were. So I always think about McMenamin's Garden of Ediacara, and as far as I'm concerned, I imagine it being a fairly fetid sort of a place. There was all kinds of dead things, because there was only really the microbes to start destroying stuff. And they stayed around on the seafloor for a long time. So the large disc-shaped things, in my opinion, are dead things which have been grown over by microbial colonies. And you'll see that inside there is structure, but there's no pattern or process to it, as far as we can tell anyway. Such forms have been described in the UK from Bradgate Park many, many years before. So there was Hediye, Blackbrookia, and Ives Hediye. Ives Hediye was the most common one. So we grouped these together as Ives Hediye morphs. So we don't italicize that, so we keep the Latinized name just to keep everything together. But we don't italicize it because basically we consider it a type of miss, if you like. Okay? So we're going to go down onto the edge of the surfaces, so we're not allowed to walk on the main flat surfaces that you can see. We'll go down there, and from the edge you'll be able to lean over the edge and see the baby fronds, which we think are part of a succession. So there were big things that were obviously there for a long time that make these big Ives Hediye morphs. And then the late colonization of that surface included microbial filaments and the baby fronds, which hopefully you'll all see, which will be one of the first examples, certainly in terms of animal life fossils, of ecological succession.
Yeah, you can cross in the middle there.
The surfaces are usually ground stained, and that's due to iron staining, probably due to the presence of pyrite earlier on in diagenesis. So there's lots of very big fossils on here, which were known for many, many years. And you can see why they were called pizza discs. So if you go along, you can kneel on the surface, I guess, if that's okay with the rangers. And when you get right down close, you might be able to see filaments, which would be about 1/3 of a millimetre wide. They can be about that long. And on various places there are very small fronds, which you have in your guide here if you want to explore. You can also look on the same surface down to the right as well. But try not to stand on the surface itself if you don't mind. So this is Pigeon Cove in the Druck Formation. So this is about 7 or 8 million years older than the main mistaken point surfaces. This surface is remarkable for these larger discoidal structures that are called Ives Hediye morphs. They were originally known from the UK under the name Ives Hediye, Blackbrookia and Hediye. And they've been reinterpreted as something like a microbial mat that's growing over a dead Ediacaran. So this would be necromass or dead organic matter on the seafloor that's largely being modified by microbial growth. So this structure inside here isn't really very organized. There are many hundreds of these and there's no real pattern to them. So these have been known for a long time through the work of Guy Narbonne and others. And recently, well fairly recently, in about 2010, we described some tiny fronds from the same surface. So if you can see here, there's a more or less spindle-shaped feature in here.
There's a form in here which is actually a charnia. And on the same surface there are these long microbial filaments, which on this surface I think are no more than about 10 centimetres in maximum length. At this locality they tend to be quite isolated. On the Bonavista Peninsula they are much, much longer and they join up much larger taxa. Initially we had discussion as to whether these might be trace fossils, but we're now thinking of them as actually microbial filaments, so giant microbes.
I'll just wave my arms a little bit here because we've been walking through a pretty interesting ecoregion called the Eastern Hyperoceanic Barrens, which is confined to the north and south tips of these peninsulas like the Avalon Peninsula and the Burin Peninsula, Bonavista Peninsula. And the vegetation here, we have a lot of Arctic alpine components in it. I mean, when I first moved here, I thought, whoa, tundra.
Yeah.
And the trees you'll see, when we pass through that little gully with balsam firs about this height, you can see that the trees are confined essentially to sheltered areas. And a lot of these trees this height, are old growth. And the reason is, in winter, the winds and the wind chill kill the tips of the trees, so that's where they can survive. And the locals call this tuckamore. So that's the famous tuckamore. This track you've been walking on was used as a cart track from a community called Long Beach, which was just beyond where we parked, to this little stream valley here, which was used to be known as Watering Cove because they brought their animals in the summer down here, now contracted to Watering Cove. And there are a couple of things you'll note here, that the color of the vegetation, this is the natural vegetation, it's called black crowberry, beloved of shorebirds in the fall because the species that come here feed on the berries and then fly non-stop to South America. You can see the grasses there, and that's the change in the vegetation from the crowberry to these grasses, and that's due to their animals grazing. And they built stages here, and they could, because it's such a rough coast in terms of wave action, they could launch their dories and fish for cod. And you'll see places like this where there are stones laid out, and these are fish flakes where they used to lay the split cod to dry. Very nice geologically too. You can see a small asymmetrical anticline here. As far as I know, the date for the closure of Iapetus and the docking of Avalonia with this portion of Proto-North America, if you want to call it that, was about 425 million years ago. And the famous D&E surfaces are exposed on both sides of Watton Cove. And when we've been to the main D&E site, we'll come back, we'll look at the E surface down here and have lunch in Watton Cove, which is a bit more sheltered. I think I'll leave it at that, Duncan. What do you...
That's perfect. We can just go on to the D&E surfaces.
Yeah.
Once you get up like up here, there's no bits like up there.
I'd really like you to take a look at the bedding cleavage relationships here, and I know you're not going to, you're going to look at the fossils. But there's an interesting story here in terms of retrodeformation and stuff, because it's certainly not as simple as uniform strain across the surface. And there are a couple of episodes of deformation. Anyway, that's my personal thing, never mind about that.
Yeah. So this is the classic, iconic Mistaken Point locality. This was discovered 50 years ago, probably more or less to the day. You can see it's in its typical weather. This is fog drifting off the Labrador Current. There are two main surfaces here, the D surface, which is just above where the geologists are, and the E surface, which is just slightly higher up. Those are the two main fossil-bearing surfaces that people think about when they think about Mistaken Point. Due to geoconservation concerns, now that we've become a UNESCO World Heritage Site, people have to put booties over their feet so there's not too much abrasion on the surfaces.
Yeah. I mean, it's got, I'm not seeing it like a storefront or anything, but it's kind of a... Oh, sorry? I can see more on that one now.
Different sort of morphological ideas.
Oh, that's incredible.
Some of them but if you've got really stable environments, you select for a particular morphology very strongly. And that means that the morphology gets produced no matter what, it gets very buffered. When the alignment is... So no one knows this.
Thank you. Sunscreen.
So we use three of them together, so that's more smooth.
So this is the D surface at Mistaken Point. The D surface has quite a low diversity. It's dominated by these long spindle-shaped forms and another curved form, which I'll have to find now. I can't see any. Oh, there's... Okay, so there's the long spindle-shaped forms, and there's the bush-shaped Braggatia, which are quite different to the ones in the UK, but people seem quite happy with that. And then there's a third taxon, Pectinifrons, which is a curved feature with lots of short fronds that come off the side. So the ripples effect that you see on the surface isn't wave ripples, these are tectonic features. The orientations of the fossils on here, particularly the Fractifusus, are more or less random. There's no current orientation that we can determine. So this was a fairly low diversity but high abundance fauna. How you interpret that is would tend to be, I guess, that it's a fairly stable community. The things are quite large in comparison to the other surfaces, so maybe there was quite a lot of time on here, and maybe this is some sort of climax community. But there are better people to talk about that than me.
So one of the biggest questions is how they made their life, so what they were doing. So there are various different hypotheses for that. So the one that's become classically entrenched recently is that they took organic carbon, dissolved organic carbon straight out of the water column and then used that. And other people have suggested that maybe they took particulate organic matter, so in a manner to like amoebae with little pseudopods, that sort of thing. And recently Duncan, McIlroy and Suzanne Dufour have suggested that perhaps they were utilising the hydrogen sulfide that would have built up underneath the front in the sediment and then harboured chemosymbionts in their tissues to combine that with the oxygen. It's very difficult to constrain exactly what they were doing, but one of the ways that you can look about it is whether there was competition between the different individuals. So between individuals of the same species and then between different species. And that's something that Emily Mitchell's been looking at. So looking at the spatial analysis of the fronds and whether you get, for example, where you get the Chinese Disqus all in a little patch and whether that's original, so for example, whether they've settled in a community like that or whether they're exploiting a shared resource. And if they're preferentially living and growing away from each other, then you can infer that they're competing for a resource. If they grow close together, then either they've settled there, it's a reproductive thing, and she's demonstrated that pretty convincingly, I think, for Fractifusus, where you get clusters of clusters of clusters. So you have like a grandparent and then a ring of children around them and then a ring of grandchildren around each of their children. Yeah, it's the way you find them together. It's either that it's a reproductive pattern, so for example they've a lot of propagules have settled in the same place, perhaps sourced from a parent nearby, like with the Fractifusus, or it could be that they're exploiting a shared resource. So where you see all the fractifusus, these spindle-shaped ones here, where they preferentially cluster around an Ives hediomorph, the suggestion is that that's a ready source of organic carbon. So that necromass, that dead and decaying tissue that's just represented now by the pimply, bubbly textures, that's actually acting as a nutrient source for the fractifusus which cluster around it. And then if other species preferentially avoid the Ives hediomorphs, maybe there's something toxic that this dead necromass is emitting that they don't like, but which the fractifusus can cope with. And it's really by looking at how the competition, well, whether there is competition between the individuals or whether there is really vertical tiering in the community. So whether you have small ones occupying a lower layer in the water column, then medium-sized ones, and then tall ones like you see in rainforests and some like crinoid communities. The tiering and the structure of the community and the different populations within the community can tell you what they were competing for. So whether that was something coming from the sediment surface or whether it was something that was vertically distributed in the water column. For me, one of the interesting things about the surfaces is how the communities are so different. So on the D surface, where you just were, you have fractifusus everywhere, all over the place, a few pectinophrons, but it's much lower diversity than this surface here, where we've got, even just in the little corner there, we've got sort of 6 or 7 individual taxa of all different kinds. And it's whether that's a succession, so the communities just had time to develop and reach greater diversity, or whether there's an environmental difference, so a different, in my mind, it's different amounts of disturbance that's helping to control the community. So in a classic idea in ecology is intermediate disturbance, so where you have some taxa that are very good at withstanding disturbance, some that can't withstand it at all, you get this kind of Goldilocks zone of diversity. So I think that's for me, that's kind of the next interesting question for me personally. But with the modern techniques that we have and applying modern ecological metrics to these ancient communities, we can get a much better idea of what they were doing and how they were living.
So this corner of the E surface was made famous by Dolf Seilacher, amongst others. And it has exceptional preservation of frondose creatures. So you see a holdfast, a stem, and a sort of fern-like frond. This is the type of a thing called Beothucus. And associated with them are the fractifusus again. Now the classic model for interpreting these things is that this was a holdfast, and the stem stuck up into the water column, and the frond was sat on top of the stem. I personally have some issues with that, in that the way that this bed is thought to have been preserved is that there was a turbidite current that came down over the surface, so a dense sea-hugging current, that collapsed these things and pressed them onto the surface. My problem with that is that in turbidite currents, there would tend to be some erosion in the lee of any obstacle on the surface. And also anything that's long and elongated would tend to swing in the current. And we have names for those structures, they're called collingia, and we never see that in association with any of these surfaces. My own idea is that this is actually a thing that is growing from a point with a stem, and then this portion of the frond may have been actually interacting directly with the sediment. So rather than being up in the water column and interacting with the benthic boundary layer, this is actually directly interacting with the sediment-water interface. The same as the spindles, the fractifusus, and the Beothucus. So some of these things are orientated. The fronds do have a current orientation, which is more or less in this direction here. But there are lots of other taxa that show no current orientation whatsoever. So my personal point of view with this is that it's very attractive to take something that looks like a frond and to want to put it up into the water column. If you want to talk about the ecology, there's all kinds of sophisticated ecology in terms of how the benthic boundary layer is tiered with things at different sizes, how they partition nutrients. But I think that the onus is upon people who want to do ecology to actually demonstrate that these things were actually up into the water column. Because I think at the moment there's much better evidence, obviously, that they were on the sediment water interface, because that's where we're seeing them preserved, rather than up into the water column. Okay, so at the first locality we went to, down at the Druck in Pigeon Cove, we saw Ives hediyes. And this is a different type of Ives hediye morph here, the circular feature. And one of the only things that will actually overlie an Ives hediye morph is this thing, the fractifusus. So it's a long spindle-shaped form, and if you zoom in detail on here, you can see each one of these is a rangiomorph frond-like element. So as you go around the surface on Mistaken Point, you can see lots of fractifusus. They're not orientated in any particular direction, but they're the only thing that will overlie an Ives hediye morph. So the model that we have for this is that, not that the fractifusus was actively seeking out the Ives hediye morphs as a source of food, but more that they could tolerate, in terms of a random spatfall, they could tolerate growing over the top of one. And the reason for that would have been that if this was decayed body tissue, all in here, it would have had concentrations of hydrogen sulfide, which is toxic to animals. And so for something like a fractifusus that is stuck on the seafloor, it can't move anywhere, it can't locomote, it would have had a buildup of hydrogen sulfide underneath its body. And this is part of the argument which we've used to suggest that these things actually harboured symbionts that actually took the hydrogen sulfide and made it into food for its own metabolism. So this is the whole type of Disqus spinosus. So on the bottom here you can see the holdfast-like structure, very short stalk, and the frond is in here with a spiky feature on the top. Now this has been called Disqus. The type of the genus actually comes from Charnwood Forest in the United Kingdom. And this is a drawing that was done by Martin Brazier of the type itself. So you can see a fairly similar sort of large disc, short stem, but in Martin's reconstruction, or not reconstruction, his drawings, you can see that there are multiple fronds from the top of the same stem. So inside all of these fronds you can see that there's small details, which would be the rangiomorph elements. In all of the specimens on this surface that are called Disqus, there's only ever a single frond. Which may mean that it's closer to the Arboriomorpha than the Disqids. So this is the same surface that we've been looking at earlier in the day. It's steeply dipping because there's a small fold in the rocks. And here, instead of the tuff being plucked off the surface, the upper surface is gradually being worn down, and it shows us the highest parts of each of the fossils. So we have some familiar elements. There's the fractifusus, and there's some beautiful examples of Hapsinophilus. Now this has previously been interpreted as being a zigzag central axis with frond-like features sticking up into the water column. But I think that this is much more like a fractifusus, something that's actually growing along the surface. They tend to abut quite closely against each other, which suggests something a bit like this. Other things on the surface are the Ives hediye morphs, these kinds of things. There are various frondose taxa. And a very large feature over here, which is kind of chambered almost, that's still problematic. We have no real idea how that might have worked. The individual elements in it are slightly triangular, which is suggestive of Thectardus, which we saw on the main surface, but that really, a triangle's a triangle, so there's not much we can do with that. One of the really interesting things about this surface is the way that it weathers down. So further up, there's a thin veneer of tuff, but right down at the bottom, it's been polished right down to the bedding plane. So this is the junction between the tuff and the sediment underneath. And what you can see in here is the ghost of the lowermost parts of the fractifusus. And that shows that the fractifusus was actually growing down into the sediment and displacing the sediment, which is part of the defense for these things actually wanting to interact with the sediment water interface with these fractal surfaces that were growing along it.